Hundreds of years back, when physicists or mathematicians would want to solve a problem, they would sit down with a pen and a piece of paper and start scribbling away complicated equations and try to solve them in a very logical and analytical fashion. Today, if you're an aspiring physicist or an engineer or a mathematician, majority of the problems are very, very difficult to solve with a pen and a piece of paper. In fact, most of the time, you might require the help of a computer to solve that kind of a problem. Therefore, it has become very, very necessary to develop some kind of a skill in some sort of a programming language or a computational package so that you can use a computer to its most effective manner in solving various kinds of physics, electronics, or engineering related problems. Out of all the packages out there, one very common, free, and very beneficial software package is Scilab. So Scilab is a free, open source, numerical, computational software package that can be used to perform various kinds of mathematical operations, numerical analysis, statistical analysis, modeling and simulating various dynamical systems, as well as performing various visualizations. Now, Scilab has been modeled similar to other very popular software packages like, let's suppose, MATLAB. And it's very easy to transfer the skills that you develop in Scilab to, let's suppose, MATLAB. But the benefit that Scilab has over something like MATLAB is that Scilab is free. You can easily download it and without any charge start performing various kinds of simulations and modeling that you, if you're an aspiring physicist or an engineer or a mathematician, would find it very, very helpful and something that can go a very long way in your career. So in this video, I'm going to give you an introduction to this particular software package called Scilab from the very beginning. So if you're a beginner, you have absolutely no idea what this is, I'm going to give you an introduction to this particular environment, to this particular platform. In fact, today's video is the first video in a 5-video lecture series in which I'm going to develop a little bit of a skill for you so that you can use it for different kinds of purposes. So today I'm going to talk about how to perform various mathematical operations, how to initialize arrays and matrices, how to perform different kinds of programs using conditional statements, conditional loops, and how to define functions. In my coming videos, I'm going to talk about how to plot or visualize different kinds of data using Scilab. I'm also going to show you how to solve first order as well as second order differential equations using Scilab. And in 2 more videos, I'm going to demonstrate some interesting physical problems. So in one video, I'm going to show you the behavior of a charged particle and how it can be modeled or simulated in the presence of electric and magnetic fields using Scilab. And in my last video, which I'm planning right now, I'm going to solve the Schrodinger's equation and demonstrate the different kinds of results that we obtain quantum mechanically using Scilab. So let's begin today's video. What you can do is you can go to Google and search for Scilab download, and it will take you to the relevant pages. You can download the relevant files for your system. And once you download it, you run, execute, and install this particular package in your system. Once you successfully install this particular software, the moment you open it, this kind of a white background window is going to open. You might have a little bit of a different structure. You might have a command history and a variable history. I don't have it right now. I have closed them, but more or less, this is what you will see. Now, Scilab offers a couple of things which I'm going to talk about in the coming few videos. So you have console, you have SciNotes or editor, you have help window, and you have graphic editor. What I have right now in front of me is what is known as the console. So you can think of the console as like a terminal window where you can perform commands straight away and get their results. So if you want to write some single line command and you want to see the results displayed, you can do so straight away in the console window. So let us start with some very simple mathematical operations like addition, for example. How do you add 2 numbers? Let us take 2 numbers, 2 plus 7, let's suppose. You get the answer straight away in the console. So you can think of the console as a calculator where you can perform various mathematical operations. So if I want to divide numbers, let's suppose 3 divided by 2, you will get the answer. If I want to say, I want to find out 2 to the power 4, you will get the answer. If I want to do anything, for example, I want to multiply, let's suppose 3.1 multiplied to, let's suppose, 5.6, I will get the answer. In fact, if you want to evaluate some complicated looking mathematical expression, let's suppose I want to add 2 with 1.5 to the power 4, and then the whole thing I put it in the numerator and then divide this with another expression, let's suppose 1 minus 2 to the power 2, and this whole thing I want to put in another expression, and I want to find the power of this expression to the power 2. Now this complicated looking mathematical expression, the Scilab can easily evaluate it in the console window. The only thing that you have to keep in mind is you need to write the parenthesis or the brackets appropriately. That means if you have a numerator, you need to put it in the relevant brackets. You have a denominator, you need to put it in a relevant bracket. If you have an expression multiplied to another expression, you need to put all of them in the relevant brackets so that the computer can understand clearly what it is that you are trying to do. There are other very similar mathematical operations that you can perform straight away. So for example, if you want to find, let's suppose, the absolute value of some number, if I want to take a negative number, let's suppose minus 6.7, the absolute value is given by ABS. So what I'm going to do is I'm going to tell you some of these very common commands and syntaxes that is going to be very helpful for you if you're going to work on this platform. Let's suppose you want to find the remainder. You want to divide 10 by 2 and you want to find the remainder. The command is modulo the number 10 divided by 2. So if I write something like this, 10 divided by 2, what is the remainder? That is what I'll get here. The remainder is of course 0, right? But if I say 10 divided by 3, what should be the remainder? The remainder is 1. Now let's suppose you want to find the square root of a number. SQRT is the command. Square root of, let's suppose, 2. You get the answer. Square root of some other number, let's suppose you want to find square root of 3. This is how you get it. If you want to find, let's suppose, the cube root or some number to the power 1 by 4 or 1 by 5, how do you do that? Well, there's a specific command for that, nth root. If you say nth root and you take some number, let's suppose 27, 3, then this is going to give me the cube root of 27. What is the cube root of 27? 3. Let's suppose I want to find out the fourth root. That means some number to the power 1 by 4 of, let's suppose, 16. Okay, 16 to the power 1 by 4. So I'll have to write 4 here. This is nothing but 2. 2 into 2, 4 into 2, 8 into 2, 16. So this is how you get this answer. There are other very interesting mathematical operations that you can also perform. Let me just show you. If you want to find out, let's suppose, the factorial of a number. What is a factorial? Well, factorial is when you take that number, multiply with its one number smaller than it, and then again and on, so you get the factorial. Let's suppose I take factorial of 5. So this should give me 5 into 4 into 3 into 2 into 1. This gives me the answer 120. You can take, you can find out the factorial of very large numbers also. Let's suppose I want to find out the factorial of 10. So 10 into 9 into 8 into 7 into 6 up to 1. So this gives me the factorial of 10, which is a very large number. If I take, of course, even bigger number than this, I take 50. Of course, this is going to be a very, very large number. So in these cases, you don't get the entire number explicitly. You get it in the form of, here you are getting it 3.041 into 10 to the power 64. So you see this D plus 64. This simply means that multiplied by 10 to the power 64. So this is essentially 3.041 multiplied by 10 to the power 64. Now, of course, you can't find factorials for any number. There's a limit beyond which you won't be able to evaluate it. For if you take very large numbers, so these kind of numbers, even Scilab cannot evaluate it because it's a very, very large number. It is actually able to do it. Let me take some other number, factorial of 1000, let's suppose. Now here you will get INF, which means that it is approximating infinity. It's of course not exactly infinity, but the system is not able to evaluate this kind of a large number because it's a huge multiplication. 100,000 multiplied by 999 multiplied by 998 up to 1. That's a huge number. So let's leave this at that. Now, as I was saying, large numbers can be demonstrated in this particular manner. So 9.33 into 10 to the power 157, right? This is written in terms of powers of 10. Similarly, small numbers, decimal numbers also can be written in this fashion. So for example, if I say 0.000000001, now this will be written as 10 to the power minus 13. So this is 1 into 10 to the power minus 13. Now there are some kind of common mathematical operations that we perform. For example, if I want to find the log of some number, log of 2, the logarithm of 2 base e. This is how you write log 2. You get the answer 0.69. Log that I've written here as a command essentially refers to the natural logarithm, which means ln or log base e. Now, if I want to find out log base 10, I'm just going to write log 10, the number, you will get the answer. If I want to find out the log base 2, I'll write log 2, the number within brackets, you get the answer. So these are predefined in the Scilab libraries, so you can make use of these predefined commands and syntaxes available to you in Scilab. If I want to find out, let's suppose, the exponential of some number, exp 0.1. So this is essentially e to the power something, right? When you write exponential within brackets something, this refers to e to the power something. So this gives us the answer e to the power 0.1. If I want to find out, let's suppose, e to the power minus 0.1, this is the answer that I get. Now, in mathematics and in physics, we use different kinds of constants, mathematical constants, which in Scilab are predefined. So for example, e, let's suppose I can call e by just writing percentage e. So if I write percentage e, this is just going to give me e that we are familiar with. Let's suppose I want access to another very important command, which is pi, that can be called by writing percentage pi. So this is 3.141. Now these constants are very helpful because many of the times we will use them in our calculations, but I don't really want to write down their value all the time, but I want to write this particular variable, you can say, which is predefined in Scilab in that particular expression. So if I have some expressions where I want to say 2 pi, so 2 multiplied by percentage pi will give me 2 pi. Let's suppose I want to write an expression 1 upon 2 pi. Okay, so what is this? So this is going to give me the answer, which is 1 upon 2 pi. There is another very important variable which is initialized here, that is percentage I. This is nothing but the imaginary number, square root of minus 1. All right, so if I write sqrt and I say minus 1, I essentially get the imaginary number. Here, the imaginary number is displayed in the complex form. So you see the I is nothing but 0 plus I. So the real part is 0 and the imaginary part is 1 times minus I. So therefore, I can also do calculations using complex numbers. So if I want to write some complex number, I'll just write the real part plus some imaginary part multiplied by this percentage I. And Scilab will consider this as a complex number. In fact, I can perform various kinds of mathematical operations like this. So let's suppose I write a number like this, which is complex. I want to multiply this with another complex number, right? I just multiply it. So for multiplication, I use the star here. Let's suppose the other complex number is 3 minus 2i. So 2 multiplied by percentage I. So Scilab is able to easily evaluate this and give me the product of these two complex numbers. Therefore, you can use this console to perform different kinds of mathematical operations that we can usually do in our day-to-day life while performing various mathematical calculations. Now, you have to keep in mind that Scilab is case sensitive. So I just now wrote you, let's suppose exponential, I said 0.1, right? I can't write exp as e capital, okay? So it won't be able to understand what this means because the Scilab platform is case sensitive. So for example, if I say capital log2, let's suppose, Scilab is not going to understand it because everything is case sensitive in Scilab, and I need to write the commands and the syntaxes and initialize the variables accordingly. Now let me also show you various mathematical functions that we use, like trigonometric functions. So in mathematics, we use various trigonometric functions like sine, cosine, tan, etc. In Scilab, it's all predefined in the library. So for example, if I say sine, I want to find sine of, let's suppose, pi by 2, right? So that can be written by saying sine within brackets percentage pi upon 2. So this is nothing but sine pi by 2. What is sine pi by 2? 1. There you have it. You get the answer. Let's suppose I want to find cos pi by 2, right? Now, what is cos pi by 2? Well, this in fact is actually 0. You see, in Scilab, we have these inbuilt sort of commands and functions which are present in the back-end libraries. But many times, Scilab gives us a particular answer by performing some kind of a numerical computation. And let's suppose here, analytically, cos pi by 2 comes out to be, or should come out to be 0, but probably Scilab is performing some kind of a numerical sort of a calculation to come up with the answer. And the thing about numerical calculations is that many times it will happen that you will end up getting a number which is very, very close to the number that you are expecting. So what is this? This is nothing but 6.123 into 10 to the power minus 17. So this is a very, very small number and approximately equal to 0. Similarly, you can also find out, let's suppose tan. All right. So tan, let me say per pi by 4. All right. What is this? This is nothing but 1. Similarly, you can perform the other kinds of trigonometric functions also. So cosec, it's CSC, okay, and sec theta, sec pi by 4 is SEC, okay. You want to find cot, the command is COT. No, cot is not defined. In some versions, I think instead of cot, you have cot G. So this cot G is for cot theta. All right. So now you must realize that the input that I'm giving to the trigonometric functions is in terms of radians. What if I want to give it in terms of degrees? So let's suppose I want to write sine something, right? Here I've written sine pi by 2, but I want to write sine 90 degrees. But if I write sine 90, it will take the argument or the input as radians, but I don't want to give it as radians. I want to give it as degrees. So for that, you just put D here, SIND, then the argument or the input will be taken as degrees. So this is going to give me sine D 90 is 1. So similarly, if I want to write cos D and I want to say 45, this is going to give me the relevant answer. Similarly, for the other commands, tan D 45, it's going to give me 1, right? Now, if I want to find out the inverse of trigonometric functions, let's suppose that is sine inverse something. For that, you can find out by writing a sine, okay? So a sine represents sine inverse of that particular number. So a sine of what? Let's suppose I want to find out a sine of 1, all right? So this should give me pi by 2. So this is nothing but pi by 2, right? So percentage pi divided by 2, the same number as this 1.57. Similarly, I can find cos inverse a cos. I want to write something here. I'll get the answer 0. So these are the various kinds of trigonometric functions that are already inbuilt in the library of Scilab that you can use whenever you're performing various mathematical operations. Now let's move ahead to variable initialization. You see, we are not here in Scilab to just use it as a calculator because you already have calculators for that if you want to perform simple mathematical operations. No. You want to perform complicated mathematical expressions that where variables are defined, right? In mathematics, we define variables, x is equal to something, y is equal to something. Well, you can initialize that kind of variables here also. So let's suppose if I say x is equal to something, some number, that means the x variable has been initialized. That means x is what is x? X is a letter, it's a character or a series of letters. Now that letter has been given a value, that value is 2. And now I can use this letter in some kind of a calculation and that value which has been assigned to that letter will be taken by the particular command. So if I say, let's suppose 5 multiplied by x, now the computer is going to take the value of the x and multiply it to 5 and give me the answer, which is 10. So this is known as variable initialization. I can initialize any kind of a letter or a string of characters and give it some value and use it as a variable in my calculation. So let's suppose I say x is equal to, so I can redefine these variables, okay? I can say, let's suppose x is equal to 20. So now x is a variable having value 20. I say y is equal to 30, all right? So y is another separate variable having value 30. And I can perform calculations with x and y. So let's suppose I say x divided by y. This is going to give me the answer 20 divided by 30. If I say x multiplied by y, let's suppose whole square, this is going to give me the relevant answer. So that way you can initialize or define variables and give it some value and use those variables in your relevant calculations. Now, I have been performing all these calculations in the console window, right? Sometimes I may have a lot of these lines written in front of me. I want to unclutter the window. I want to remove everything that I've written. I want to erase everything that I've written. So for that, I have a command called CLC. So what CLC does is it clears the display. CLC clears the display that is in front of me. It erases it, gives me a clean screen looking neat and tidy for me to perform a program. But what CLC doesn't do is it doesn't erase the variables that I've initialized. So right now I have initialized a variable x, right? Remember, I initialized a variable x. If I enter x, it will give me the value of x, which I already defined just few moments back. What if I want to erase this? What if I want to erase all the variables that has been defined in my command history? For that, I have a command clear. If I type clear, then this doesn't erase the display, but it erases the variable history. The variables that has been defined in the session memory, those variables gets erased. So now if I type the same X, it's going to give me undefined variable. So sometimes if you want to erase the variable history, use the command clear, or if you want to erase the display only and not the variables, type CLC. Now let's move ahead to another very powerful feature in Scilab, which is initializing arrays and matrices. Arrays and matrices are very, very important in mathematics and physics for performing different kinds of calculations. So Scilab is very comfortable with those things. So if you're working with arrays or matrices, you can easily initialize them in the Scilab platform. So for example, if I say X is equal to, I want to define an array. All right, first of all, what is an array? An array is a list of numbers or a set of data points, or you can think of it as a row matrix or a column matrix. All right. Sometimes arrays can also be a list of strings of characters, but most of the time we use an array as a list of data points or a set of data points, right? So for example, I have a couple of data points, 1, 2, 3, 4. So what I'm going to do is I'm going to write 1, 2, 3, 4, but I'm going to put it within square brackets. The moment you put something within square brackets, it specifies to Scilab that you are trying to write an array or a matrix. So I'm putting 1, 2, 3, 4 within square brackets. Now I'm separating these numbers with space. It's important to separate these numbers with space, or you can also separate with a comma. For example, if I separate with a comma, then it takes these as different elements. Okay. So if I enter it, I get an array. So I can create any kind of an array. So I can say, okay, let's suppose X is equal to any kind of a number. I want to put 0.1, 2, 4.5, 6, -1, 5. So this gives me an array, a list of numbers that I have initialized as X. Now I can also, in certain cases, specify an array as a collection of a string of characters. So what are strings of characters? Strings of characters are different from variables because variables had certain values, numbers associated with it. But strings of characters are just words or letters written in the form that I'm going to give it to this particular system. So for example, if I say X is equal to, I want to write the capital of a couple of countries. So I want to write, let's suppose, New Delhi within single inverted commas. So it specifies, the single inverted comma specifies that it is a string of characters. I want to give it a space. I'm going to write another, let's suppose, capital of US, let's suppose Washington, DC. And I'm going to write another capital of France, let's suppose Paris. So this gives me an array containing strings of characters, which might be helpful in certain situations later on when we are performing programs. Now arrays are very, very helpful, especially arrays of numbers is very helpful if we want to define a range. Let's suppose I want to define the x-axis or the y-axis, and there is a large number of data points in that range. Arrays can be very, very helpful in specifying those data points. But I cannot just write 100,000 numbers with my own hands, right? So I can write, let's suppose X is equal to 1, 2, 3. It's fine, but I want to write from 1, 2, 3 up to 1,000. What I'm going to do? Well, there's an easy way of doing that. Instead of writing 1, 2, 3, I can say array X is equal to within square brackets 1 colon. If I say, let's suppose 10, okay, I don't want to take 1,000 because it's going to fill my whole window with lots of numbers. I say 1 colon 10, it's going to give me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's going to give me an array, a list of numbers from 1 to 10 with the default step size of 1. If I want to change the step size from 1 to, let's suppose, I want to go from 1 to 2 up to, let's suppose, 9. So I'm going to go from 1, 3, 5, 7, 9. This is going to give me an array or a list of numbers from 1 to 9 with a step size of 2. I can take any kind of a step size I want. Let's suppose I want to take 0.2 and I want to go from 1 to 2. This is going to give me 1.2, 1.4, 1.6, 1.8, 2. All right. So you can generate an array very easily in Scilab just by using these kind of commands, and they are going to be very, very helpful later on when I want to sort of define a function, differentiate a function, plot some function, or evaluate some sort of a data in a very large set of data points. These arrays are very, very important. Now this brings me to matrices. You see, arrays are nothing but row matrices in a way, right? But I can in general write matrices. So let's suppose I've been using X, right? Let me write A as a matrix. Okay, so if I want to define a matrix, I need a couple of rows. I say 1, 2, 3, which is the first row. I'm going to separate the first row from the second row with, let's suppose, 3, 4, 5. That's it. This is a 2 cross 3 matrix. If I want to write down another matrix, let's suppose I want to specify or add another row to it. I'm going to put 4 and 2 and 1. This is a 3 cross 3 matrix. How easy it is to initialize a matrix in Scilab. Now, if you may have performed other basic programming languages like, let's suppose, C++ or Fortran, you may remember that initializing matrices is a very difficult and very laborious process. You have to use for loops. For I is equal to something something, for j is equal to something something. You have to give the numbers, the elements separately, and then perform the operations and then display the matrix. It's a very laborious, lengthy task, right? But in Scilab, it's very easy to initialize a matrix. In fact, it's very easy to perform calculations with matrices. So let me give you an example. So let me clear the window. Let me clear all the variables here. And let's suppose A is equal to, let me take a very simple matrix, 2, 3, and semicolon 4 minus 1. This is a 2 cross 2 matrix. Sorry, this is not the one. I forgot to put the semicolon here. Put the semicolon here. This gives me a 2 cross 2 matrix. Let me define another matrix. B is equal to, let's suppose, 1, 5, semicolon 6, and 2. All right, this is another 2 cross 2 matrix. I can perform various operations in matrices. For example, if you want to add these two matrices, you just do A plus B. That's it. You will get the sum of these two matrices. If you want to subtract A minus B, that's it, right? A minus B, you get this subtraction of A minus B. Now, of course, whenever you're dealing with matrices, you'll have to make sure that some of these operations make sense. So for example, if you multiply two matrices, you have to make sure the order of the matrices are appropriate so that a matrix multiplication makes sense. Here I have 2 cross 2 and 2 cross 2 matrices, which are A and B respectively. So I can multiply them. So A multiplied by B, this gives me a multiplication of both these two matrices. There are various kinds of things we can do. Let me show you a few of them. So what is A? Let me clear the console here again. What is A? A is this and B is this. Sometimes, in some cases, we are interested in doing element-wise operations. So A is 2, 3, 4, minus 1. B is 1, 5, 6, 2. But I don't want to multiply the matrices. I want to multiply the individual elements belonging to the same position. So I want to multiply, let's suppose, 2 with 1. I want to multiply 3 with 5. I want to multiply 4 with 6 and minus 1 with 2. This is not matrix multiplication. This is element-wise multiplication. The way to do it is you do A star B, but you put this dot in front of the star. So whenever you are dealing with arrays, you perform an operation of one array with another array, but you do not want to do a matrix operation. You want to do some sort of an element-wise operation. What you do is you put a dot in front of it. The moment you put a dot in front of it, the computer understands that you're doing an element-wise operation. So this is going to give me an element-wise multiplication. You see, 2 multiplied by 1 gives me 2. And 4 multiplied by 6 gives me 24. This is not matrix multiplication of A and B. This is element-wise multiplication of A and B. Individual elements multiplied accordingly with respect to their positions. I can also do other operations, element-wise operations. So if I say A dot to the power 2, I'll simply get 2 square, 3 square, 4 square, minus 1 square. Okay. So this is an element-wise operation of this kind of a matrix. There are many sort of operations which are predefined, commands which are predefined in Scilab, and it's very interesting. Let me demonstrate a few of them. So I have this matrix A, right? If I want to add all these elements, 2 plus 3 plus 4 minus 1, I'll just say sum A, and this is going to give me the sum of all these elements. If I want to find out the average of all these elements, I'm just going to write mean A. It's going to give me the average of all these elements. If I want to normalize this, let's suppose I want to find the square root of the sum of the square of these individual elements. So I'll use the command norm of A. If you're familiar with it, you will know what this is. So this gives me norm. If I want to find out, so this A, if I want to find a maximum number, or rather the largest number here, I'm just going to type max of A This gives me 4, which is the largest number here. If I want to find the smallest number, I say min of A. This is going to give me the smallest number. What if I want to transpose a matrix? Again, let me clear the console. A, this is the matrix. I want to transpose it. You know what transpose it, right? You interchange the columns and the rows. So that is very simple. A dash. That's it. And you get the transpose of the matrix. What if I want to find the inverse of a matrix? Now, remember, if you are familiar with any kind of a basic programming languages like Fortran or C++ or Python, how difficult it is to find the inverse. How lengthy a program you'll have to write to actually find an inverse. You input the numbers of a matrix, you perform certain calculations, you display the result. It's a very lengthy process. In Scilab, it is like magic. I and V, the matrix, you get the answer. This is the inverse of the matrix A, straight away. Just like a complicated calculator, you can find out. See how beautiful it is? If you want to find, let's suppose, the determinant of A, DETA is a command for that. DETA, you get a determinant of the matrix A. There are various things you can do here. Let's suppose, again, let me clear the console. You have this matrix. I want to find just the diagonal elements. What are the diagonal elements? 2 and minus 1. So I'm going to say DIAG. This is going to give me the diagonal elements of A. Now, this is not something that you can do only for 2x2 matrices. You can also do it for 3x3, 4x4, 5x5 matrices. I'm just showing you the commands that can be used for any kind of a matrix as long as it makes sense mathematically. Let's suppose I want to extract the first row of this matrix. So I want to extract, let's suppose, the first row. What I'm going to do is, see, every single element in that matrix has an index or a position associated with it. In Scilab, the very first element has a position of 1, 1. Okay, just keep it in mind that in Scilab, in a matrix, the very first element has a position of 1, 1. In that row, the other numbers are 1, 2, 1, 3, on and on. And then again, in the next column, you'll have 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, like that. So these are the positions of that particular matrix. So if I want to, let's suppose, find out a row, or let's suppose I want to bring out an element. Let's suppose I want to bring out the second element here. Okay, so I'm going to just say 2, 1. I'm just going to specify the position of that number, and it's going to give me, 2, 1 is this one, right? 2, 1, second column, first row, this one. I was talking about, let's suppose, A, 1, 2. So this will give me this particular number 3. So A, 1, 2, that's it. If I want to find out, let's suppose this one, 2, 2. So if I say A, 2, 2, this is going to give me this particular number. So if you want to extract a number or an element from a matrix, this is how you do. Matrix, within brackets, you specify the position such that the first element has a position of 1, 1. Again, if I want to, let me clear the console, just a moment, let me clear the console. If I want to extract a row, what I'm going to do is A, 1, colon. 1, first row, colon means all the elements of the first row. You get the first row, which is 2, 3. If I want to extract the first column, I'm going to say A, colon, 1. That means first column, all the elements of the row. That's it, 2, 4. This is what you get. Now, certain kinds of matrices that we use are already predefined. So for example, if I want to write a matrix having all the elements as 0, so I'm going to say command ZEROS, and I'm going to write the size of the matrix. Let's suppose I want a 3x3 matrix having all the elements 0. I'm going to write ZEROS. This is going to give me a 3x2 matrix, 3x3 matrix having all elements as zeros. Let's suppose I want all the elements as 1s, and I want a 2x2 matrix, EYE. No, sorry. This is a command for an identity matrix. I'm very sorry, not for all the ones. This is a command for identity matrix. EYE, if I want a 3x3 identity matrix, EYE 3, 3. This is an identity matrix where you get all the elements in the diagonal as 1. But if I want all the elements as 1s, so let's suppose I say 3, 3, 1s. So this will give me all the elements of 1. Now, matrices are very useful in physics and mathematics because they can be used to solve different kinds of problems. A very simple problem is to solve a system of linear equations. You must have studied that if you want to solve a system of linear equations, you can represent that system of linear equations in the form of a matrix and then solve that particular matrix problem to get the answer. So for example, I have with me a system of linear equations. So 3x plus 2y minus z is equal to 1, 2x minus 2y plus 4z is equal to minus 2, minus x plus 0.5y minus z is equal to 3. So we can represent this system of linear equations in the form of a matrix equation of the form ax is equal to b. Now the solution to this system of linear equations is x, which is equal to a inverse b. So if I specify a and b as matrices, I can easily get the answer to this system of linear equations. So what is a according to the system of linear equations? Well, a is equal to 3, 2, minus 1 is the first row, 2, minus 2, 4 is the second row, minus 1, 0.5, and minus 1 is the third row. This is A. And what is B? B is a column matrix. So you have 1, second row you have minus 2, and the third row you have 0, right? So the system of linear equations, as you have seen, can be solved by writing A inverse, okay, A inverse INVA multiplied by B. This is the answer. The solution to the system of linear equations is x is equal to 1, y is equal to minus 2, and z is equal to minus 3. So you see how powerful this is. You can simply solve a system of linear equations using this particular command in this manner in Scilab. I've just done it for 3 system of linear equations. You can do it for n system of linear equations. So the console is a very powerful platform to perform all these different kinds of mathematical operations dealing with numbers or arrays or matrices. But we are not here to use Scilab as just a simple calculator to perform simple mathematical operations. No, we want to write multi-line programs to perform very complicated sort of task. Because what we are doing here right now is we're just writing one single line command and executing it, right? But programming is not just writing a single line command. It's to write complicated multi-line commands to execute some sort of a logical operation. To do that, we must go beyond the console to another platform which is known as SciNotes. But before I go into SciNotes, let me show you one thing, that if you are interested in figuring out some sort of a command or a syntax to perform an operation, what you can do is in the console you can write help, H-E-L-P. If you ask for help, help shall arrive. You see this new window gets opened up, which is essentially the help browser. Here you can go into the search and you can type anything you want. Let's suppose you want to find the command to find the log of something. Here you search and then you get different kinds of options in the left hand side. Log 10. So this is basically the syntax for finding the log base 10 of some number, and you will get the relevant information about that particular command and some relevant commands related to that. So if you are interested in finding out some kind of a command or a syntax to perform some operation, you can always go into the help browser and type in that particular command or something related to that search name and sort of browse and figure out that particular syntax for yourself. All right. You can access the help browser by typing help in the console, or you can just, you see this question mark here. You click on the question mark, you see Scilab help. You click on Scilab help, the help browser will open. Now let's close the help browser because I'm the one who is here to help you right now. So you can browse the help browser later on. So to write multi-line programs, we need to go from the console to something that is known as editor or SciNotes. And to do that, I'll have to type editor, editor, and this new sort of a window opens up. Let me close this earlier window I had. So this new window opens up. You see this? What is this? This is the editor or SciNotes. Now, how is the SciNotes different from the console that I was working on? Well, as I said initially, the console is like a terminal window where if you perform a single line command, it gets executed and displays the result immediately. SciNotes, on the other hand, is like a notepad. Here you can write anything, like any kind of a command, but it won't get executed and the results won't get displayed immediately unless you save the program and run it separately. Right. The beauty of this is that we want to perform multi-line commands and it takes time to build up a program accordingly. So here I am going to type in that particular program, save it and run it, and the result of that particular program will then be displayed in the console. So let's keep the console to the side and let's focus on the SciNotes here. So let me show you how to write a very simple program in Scilab. All right, the first program is the universal beginners program that people demonstrate everywhere. So let me do the same thing. Hello world. I want to demonstrate hello world. But before I demonstrate hello world, let me sort of clear the sort of console. I can clear it from here itself. I can clear it from there. So let's suppose I type clear. It clears the variable sort of memory, the session memory, and CLC, it sort of cleans up the display. Now, I want to display some string of characters that says hello world. So the command for that is disp within brackets. For a string of characters, I have single inverted commas. I'm going to say hello world. Now to run this, first I need to save it. All right, I'm going to save it somewhere. So you save it somewhere. Let's suppose I say this is a test 1. I saved it and I executed it, but I don't see anything happening. Well, I see the results not in the editor. I will see the results in the console. So here you have it. This is the console. That's it. The most simplest program of all has been executed right in front of you. Display hello world. But you're not learning Scilab just to write hello world. You want to do much more complicated mathematical problems. So let me show you the most simplest version of that. Let me perform a mathematical operation. Let's suppose I initialize a variable x is equal to 10, and I initialize another variable y is equal to 2, and I say z is equal to x plus y. Okay. Now I want to display the z. I will have to display z. Okay, I can just write z is equal to x plus y, because if I write z is equal to x plus y and then I sort of save and execute it, I don't really see anything in the console window because z is there. By the way, if I type z, the answer has been achieved, but I need to specify a separate command just to display the result. So for that, I'm going to say disp z. If I run this, then I'll get the answer, which is 12, right? 10 plus 2 is equal to 12. Now let me bring the console to the left hand side and let me bring the SciNotes to the right hand side. So here I can write the programs, and the left hand side you can see the results. All right. Now I can make this program a little bit more complicated in the sense that I can ask the user to enter 2 numbers, and then the program will add them and give it to you. So instead of writing a number here, I'm going to say input. Input basically is a command to ask the user for some sort of an input. So, and the input is followed by some kind of a message so that the user knows what to input. So I'm going to say enter, ENTER, first number. Okay. Okay. And for Y, I'm going to say input within single inverted commas. I'm going to write a message, enter second number. Now, if I run this, the program asks me, the user who has run the program, to enter a number. So let me enter anything, 6.7, right? Now it's asking me enter a second number. Let me write 4.2. And then it gives me the answer of 6.7 plus 4.2. But I'm going to write another message with the result. So let's suppose I'm going to say, I'm going to add a string of characters. So how do you combine strings of characters and variables? Because Z here is a variable, but I want to include a message that the result is Z. So how you do that is within the disp command, within the brackets, you write the string of characters followed by the variable, you separate them with a comma, right? So when you run this, enter the first number 5 and the second number 6, the result is 11. Now the thing about the disp command is that the string of characters here and the variable is separated by a line in the sort of a console, right? They are in separate lines. What if I want to write them in the same line itself? Then you'll have to convert the variable into a string of characters. So for that, what I'm going to do is I'm going to say string Z. So Z has been converted to a string of characters, and I'm going to add this string with the earlier string of characters by plus. You see this? So here I have the string of characters, right? And Z was a variable, but I've converted that to a string of characters. And then the plus basically combines these two things. If I run this, then enter the first number 3 and the number 5, the result is 8. That's it. This is a very simple program to ask the user for some input and take those numbers as variables and perform some sort of a mathematical operation and display the result. I have just added 2 numbers. You can do any kind of a mathematical operation. I have demonstrated so many different kinds of mathematical operations just few moments back. You can do all of that, combine it, and come up with some very interesting sort of a program to display some sort of a result. Now let us move ahead to something much more powerful in programming, which is conditional statements and conditional loops. Now, what are conditional statements first? Well, you see, in a program, sometimes I do not want to perform or execute all the lines of code. Sometimes I want to execute only a couple of lines of code based on some condition which is being met, and sort of ignore certain lines of code if certain condition is not being met. So the most simplest way of doing that is, let me show you by writing a program. I'm going to include clear and CLC every time, because every time I run a new program, I want everything else to be erased which was done earlier. Okay. So the structure of a conditional statement is basically if some condition, then execute these lines of code, else execute something else, end. So if the moment I enter it, I get this structure. If some condition is being met, all right, I have to write a condition here, then execute certain lines of code. So let's suppose I want to write a program that is going to tell me that enter your age, and if my age is greater than 18 years, it's going to say you're eligible to drive a car, or if my age is less than 18 years, you're not eligible to drive a car. So let's suppose I have a variable here. Let's suppose variable is AGE, and age is equal to 34. So if I say age is greater than equal to 18, then execute a certain line of command which is display the message that you are eligible to drive. I have to enter else also. If this condition is not being met, what is going to happen? Else, I'm going to enter another condition. Age is less than, let's suppose, 18. I don't need to write then in this case. For all cases other than the initial case, you are not eligible to drive. So this is a very basic example of a conditional statement. If certain condition is being met, then execute these lines of code. Else, if this condition is being not met, so for this case, basically I don't actually have to write this, because else simply excludes all the cases where this condition is not being met. You just write this, execute these lines of code, end. So here age is equal to 34, which is greater than 18, therefore you are eligible to drive. I can include multiple statements here. So for example, let's suppose I basically want to include the cases where age is less than 0, which is not really possible, right? So for example, if I ask the user to input a number and I say INPUT and enter age, then the program is essentially going to ask the user for his or her age. So enter your age. If the user enters some invalid number, then I want some command like please enter a valid number or something like that. So for that, I want to include more than 2 sort of conditions. So else if age is less than equal to 0, then display please enter a valid age. Else, for all other cases, display you are not eligible. All right. So this 3 sort of conditions will, I think, cover the entire range of conditions possible. So if I run this program, the program asks for my age. If I say, let's suppose 20, automatically you are eligible to drive. If I run this program again, it asks for my age. I write 10, you're not eligible. If I again run this program and I say -5, it's going to say, please enter a valid age. So I've created a very logical and sound program that asks for a particular number, an age, and based on what you enter, it gives a sequence of messages accordingly. Now, depending upon what the nature of the condition is, other kinds of logical operations are also possible. So this is a symbol for greater than equal to. This is a symbol for less than equal to. You have other symbols also for greater than, less than, not equal to that I am showing here in front of you. You can use them whichever is necessary accordingly in your program. Now, sometimes you want to combine multiple statements. It's not enough to just have one condition. You want to combine multiple conditions. How do you do that? So for example, if I want to write a program which not only tells me if I'm eligible to drive, it's also going to tell me if I'm eligible to apply to the army, let's suppose. So it's going to ask me for my height, okay, h. So let's suppose h is input your height, okay, in feet, let's suppose. Enter your height in feet, HEIGHT. Now I want to create a scenario where it's going to look for all the different kinds of cases. So for example, if age is greater than 18 and, so this is a Boolean operation where I'm going to combine two conditions. If both the conditions are being met and h is greater than equal to 6. So what is happening here? This is one condition. This is another condition. The AND combines both the conditions with some sort of a Boolean operator, which simply means that both the conditions must be true. If both the conditions are true, then execute some command. Okay, so what I'm going to execute, I'm going to display you're eligible to drive and army. There are other kinds of similar Boolean operators also for or, for not, that you can use accordingly. But in our program, if I want to sort of combine all the different cases, so if age is greater than 18 and height is greater than 6, you're eligible for driving and for army. Else if, let's suppose, age is less than 18, or let me modify it slightly. If age is greater than equal to 18 and height is less than 6 foot, you're eligible for driver's license but not army. And else if age is less than 18, or let's suppose age is less than 0, then I'm going to say display enter a valid age. Else for all other conditions, you are not eligible for either. I think these conditions are sufficient. So if I execute this particular program, this program is going to ask for my age. Let's suppose the age is 20. It's going to ask for my height. Let's suppose the height is 5 feet. You are eligible to drive, but you're not eligible for the army. You see this? It's easy to write a program in this kind of a manner where, based on whether certain conditions are being met, certain lines of code is only being executed to display a specific message. So this is the use of conditional statements. Let's go ahead to what is known as conditional loops. Sometimes we want to perform some kind of an operation over and over and over again in a very repetitive manner. So we want to perform repeated iterations of a certain lines of code. For that, we need conditional loops. So let's erase this and create another program. So let's suppose I'm going to show you first the while loop. So what is a while loop? So while some condition is being met, execute certain lines of code. So let's suppose while some variable I is less than, let's suppose 10, I'm just giving you an example. Okay, initially let's suppose I is equal to 2. While I is equal to 10, then display I. This is a very simple example of a conditional loop where I want to perform in a repeated fashion certain lines of code until certain condition is not satisfied. So here the condition is I is less than 10. So is I less than 10? Well, I is initially 2. So of course I is less than 10. Therefore I is going to get displayed. Again it's going to go back. Is 2 less than 10? Of course it's going to display. Again it's going to go back. Is 2 less than 10? Of course it's going to go back, on and on. Now this is going to run infinitely in a loop. I don't want that. I don't want my computer to hang So I'll have to put an end to it somewhere. So what I'm going to do is I'm going to write this I is equal to I plus 1. What this does is, first of all, when I is less than 2, the first time the computer executes this line, it's less than 10. Yes, displays this. Now, 2 plus 1 is equal to 3. So again, it goes back. Is 3 less than 10? Yes, displays 3. Now, 3 plus 1, 4. Is 4 less than 10? Yes, it displays it. Now again, 5, 6, 7, 8, 9, 10. The moment this becomes 10, it ends the program. That's it. So if I run this, what should you expect? Well, this is what you expect. 2, 3, 4, 5, 6, 7, 8, 9. So essentially what I have done is I have written a very simple command or set of commands, or I made a program to execute a couple of lines of code over and over and over again. Now you may say, sir, but why do we need to do that? Well, the reason is that the computer is very, very good at performing very simple operations large number of times. When I say large number of times, I'm talking about hundreds and thousands and millions of times in a microsecond. And you can't do that. For example, if I say add up the first 100 numbers, or add the first 1,000 numbers, or add the first 10,000 numbers, how much time is it going to take a calculator and add 1 plus 2 plus 3 plus 4 plus 5 plus 7 up to 100,000 or whatever? But the computer can do the same repetitive, robotic, mundane work of adding 10,000 numbers in a microsecond. How can I do that? Well, let's suppose here I say I is equal to 1. All right. And I say something like S is equal to 0. So as I is less than 10,000, instead of displaying it, what I'm going to do is S is equal to S plus I. So every time this loop runs, the I, which is incrementing every time the loop runs, gets added to this variable S. So ultimately, I'll get the sum of the first 10,000 numbers if I write it like this. So let's say I want to write display S here, and I run this, I get the answer. In a microsecond, I get the sum of the first 10,000 numbers. Now, how easy that is for the computer, but how hard that is for a human being to do. This is why computers are so very relevant, because it can perform these very mundane but complicated operations in such a simple manner. So performing this kind of a program, which involves some repetitive sort of or iterative condition, gives us or opens up a whole possibility of performing different kinds of mathematical operations. So I can not only add the first 10,000 numbers, I can multiply them. I can do many things. I can add the first 10,000 numbers, even numbers. Okay, so what I can do is I can say I is equal to I plus 2. So it increments in 2. So first I have 1, then I have, for even numbers I'll have to have 0 here. So first it adds 0, then it's 2, then 4, then 6. And what do I get? The sum of all the even numbers up to 10,000. So this is a while loop. Now, while loop provides you a very strong, powerful way of performing various iterations of code based on some condition that comes as a result of this particular program itself. Now, in the while loop, the iteration is specified by a particular line like I is equal to I plus 1 or something like that. Okay, so that at some point in time, this particular program will stop. Yes, I don't want it to run infinitely. But sometimes we already know how many number of times I want to run a set of lines of code. In those cases where we already know that I want to run a set of lines of code 10 times or 100 times, it's better to use what is known as a for loop. Okay, instead of a while loop, I'm going to use a for loop. So for, I don't need to initialize I now because I can initialize within for itself. So for I is equal to, let's suppose 1 to 10, display I. That's it. What this does is it runs these lines of code for I is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the list of numbers you get. You see this? That's it. It's easy. For 1 to 10, if I want to define the step size, let's suppose I want to go from 1 to, let's suppose 0.1 and up to 2 I want to go. So 1, 1.1, 1.2, 1.3. That's it. 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.92. So the for loop provides us with a similar sort of functionality, just like the while loop, The only difference is that in the while loop, sometimes we are not really aware how many number of times I need to perform a particular set of code, and I execute some condition within the program that will determine how many number of times the set of lines of code are going to run. But in the for loop, I initialize initially only, or I initialize in the beginning how many number of times the set of lines of code are going to be executed. So I can use this to perform anything, just like I want to add a couple of numbers. So again, same thing, right? Let's say s is equal to 0. I want to add the first 100 numbers, right? So I want to say for I is equal to 1 to 100, I want to add, so s is equal to s plus 1, and at the end of the day, or and in the program you say disps, this should give me the sum of the first 100 numbers. That's it. Sorry, I'm very sorry. This is not the sum of the first 100 numbers. This is the sum of 100 times. I should have written I here. So if I write I, s is equal to s plus I, so I is getting added every time. 1 plus 2 plus 3 plus 4 plus 5. And this gives me the sum of the first 100 numbers. I can do anything I want. I can multiply the first even numbers up to 100. I can create some kind of a series that I'm interested in. For example, you must have heard of the Fibonacci series. It's a very common, very popular series, the Fibonacci series, where every single term is the sum of the previous two terms. It starts with 0, 1, 1, and then every single element is the sum of the previous two elements. So what if I want to generate the Fibonacci series for the first, I don't know, 10, 20 terms? How can I do that? Well, let me show you. I can use a for loop. The for loop is very powerful in that sense. Let's suppose I want to show the Fibonacci series for the first 15 numbers. Okay, I want to go from I is equal to 1 to n. So I want to go from 1 to 15. What is the command? Well, let me deal with arrays here. It will be easier for me to deal with arrays. So let's suppose A, what is the first number in a Fibonacci series? So F, I say. F is F1, the first number. So the position for the first number in an array is given by 1 and not 0. Okay, the first number is 0. What is the second number in the Fibonacci series? It is equal to 1. Now here I'm going to say that f of I, so essentially f is an array, okay, and I'm specifying the elements within that array. So f of I is equal to f of I minus 1 plus f of I minus 2. So every element in that array f is a sum of the previous two elements in that same array f. Okay, I've already specified 1 and 2. I don't want to start from 1. I want to start from 3. This should give me the Fibonacci series. So DISP, the array f, this should give me the Fibonacci series. There it is. This is the Fibonacci series for the first 15 terms. 0, 1, 1, 2, 3. So essentially, the number, let's suppose 21 is the sum of 13 and 8. The number 55 is the sum of 34 and 21. The number 144 is the sum of 89 and 55. And how easily we have done it? I can go up to, let's suppose, 50 numbers. I can generate the first 50 numbers of the Fibonacci series. Well, of course, it becomes very huge in a short period of time. But this is the Fibonacci series. You see this? You see how powerful these loops are? These conditional loops? You can use that for different kinds of purposes. So I have introduced so many things in today's lecture. Let me end today's video by showing you another very powerful possibility in Scilab is how to define functions. We can define functions according to our own way and use them in our relevant programs. So let's erase all of this. Okay, let's erase all this and let me show you how to define functions. Functions are very, very powerful because you can use functions to define some sort of a mathematical function that can later be used for plotting, for visualizations, for solving differential equations, for integrations, etc., etc. And to define a function is very, very easy. You just type function and let's suppose you define the output and the input. Let's suppose f of x. I'm going to use the common symbols here. What is x? X is the argument or the input. What is y? Y is the output. What is f? It's a name of the function. You can write anything here. You can say f name or whatever. And the moment you call this f name, that function will be called, and whatever relationship x and y has, it will be performed on whatever however you write it. So for example, if I say the relationship between y and x is equal to x square. So now what has happened is that this specifies a particular relationship between the input of f name and the output. So if I run this and I say, and I essentially call this particular function, all right. So if I call this particular function f name, and I within brackets say, let's suppose 0.2, that means I'm giving the input 0.2. This 0.2 will experience this kind of a operation, and the answer I'll get is 0.2 square, which is 0.04. That's it. So therefore, this opens up a possibility of defining functions in any way I see fit. You see, some time back, I showed you mathematical functions which are already predefined in the library of Scilab. Now, many times you might need to define something according to your own sort of requirement. Then you can use this very powerful thing. I can use any kind of an expression, right? I can even apply a function on array. So for example, let's say I say a is equal to some array. So 1, 2, 3. I want to do 1 square, 2 square, 3 square, right? So I'll say f name, which is basically the name of the function. I'm calling the function here, and I'm going to say a, and this is going to give me 1 square, 2 square, and 3 square according to this particular function. You see, interesting, right? I can do a sort of a multivariate function here. Now you have to keep in mind that x and y are not variables here. If I type x, it's going to give me undefined variable, because whenever I define a function and I use x, y, a, b, c, whatever I want to use, these letters are only defined within the context of the function, and they are not defined in the variable history or in the session memory. So x as a variable or whatever other variables I use, I must define separately in the program, and writing here within the function is not sufficient. Here x and y only is used to give us a relationship between the input and the output essentially, and they are not variables that are defined in the program. So let me create a function, a very interesting function, to solve a quadratic equation. You know what quadratic equations are, right? So let's suppose that I have a quadratic equation and I want to name this function as quad, and I have input. The input is for an equation like ax square plus bx plus c, the input is a, b, c. But the output are the roots. Let me say the roots are p, comma, q. So essentially, this function is going to give me a relationship between ABC and PQ. Now, what are the relationship? Well, if you know quadratic formula, what is p? P is equal to nothing but minus b plus square root of b square minus 4ac divided by 2a, right? Divided by 2a. This is the root of a quadratic equation divided by 2 star a. So this is one root, and the other root is, let's suppose, b minus square root of b square minus 4ac, the whole thing divided by 2a. Okay, I made a small mistake. This is supposed to be q. So this is the first root p, and this is the second root q. So again, if I run this command where this is the input and the output is initialized as two separate variables r1 and r2, then I should get these two results, which are the roots of this quadratic equation 2 and 3. So you see this provides us with a way to define a function according to our own way and call that function to perform some sort of an operation from a separate program, even if I wanted to. Functions open up the possibilities of multitude of things. So if let me erase this thing and let me go back to our original sort of the program, which was the f name, okay, that I initially defined. Y is equal to fx or fx, let's suppose, and y is equal to x square. Before I leave today's video, let me show you something even more interesting. I can do various things with functions. You know, what I can do is, let's suppose if I want to differentiate this function at a particular location, I can do that. I can evaluate this function. So evaluation is, I have already showed you. Let me show you one more sort of alternative. So f of 0.2 gives me the function evaluated at 0.2. Sometimes this command may not work. If it doesn't work in your system, you can type f eval 0.2 comma f. or any number comma f, this evaluates the function at that location 0.2 and gives you the answer. If I want to find out, let's suppose the derivative of the function num derivative, and I'm going to say the function f comma some number, let's suppose 2, at 2 the num derivative is this. So what is the derivative of x square? 2x at 2 is equal to 4. If I want to integrate intg between the range of 0 to 2, this particular function f, I can do that, and this is the answer I get. So functions open up the possibilities of doing so many important things. So this is kind of an introduction to the very powerful and free software called Scilab, and I have introduced to you today how to perform mathematical operations, how to initialize variables, initialize matrices, arrays, how to use conditional statements, conditional loops, how to define functions, and it opens up the possibility of performing so many different kinds of interesting programs. I hope that you have learned all these things. You have followed me till the end of this video. If you have done so, I'm very sure that using these things you can start your own journey in programming in Scilab. In the coming lectures, I'm going to do a couple of some interesting things. In the next lecture, I'm going to show you how to plot, how to visualize data, how to plot 2D graphs, how to plot 3D surfaces. I'll show you how to solve differential equations, and I'm going to use it to perform the solution of a Schrodinger's equation. I'm going to do that for the case of a harmonic oscillator and an infinite squirrel potential. So it's going to be an exciting 3 to 4 lectures. So stay tuned. I am Divya Jyoti Das. This is For the Love of Physics. Thank you so much. I'll see you next time.